Today, my presentation is on the contraction of the magnetic island during magnetic reconnection. Magnetic reconnection is best explained through the following animation. The dissipation in the current sheet allows the magnetic flux to diffuse through, canceling the flux from the opposite side. Then the plasma is pulled out by the magnetic tension and reconnects with the field lines on the other side. This becomes a self-sustaining process due to the drop in magnetic pressure. I was provided a three-dimensional particle and cell simulation by Dr. Chair, which I utilized for my data collection. The simulation domain has dimensions x, y, and z by 64 di by 16 di by 0.25 di, with grid numbers 81, 92, 2048, and 32 respectively. Di is the ion inertial length, which is expressed as the speed of light over the ion plasma frequency. The ion inertial length is the scale at which ions decouple from electrons and the magnetic field becomes frozen into the electron fluid rather than the bulk plasma. The simulation time was 35 omega IT, with omega I as the ion gyro frequency. I started analysis at 15 omega IT, as that was where the magnetic reconnection initialized. The left half of the simulation, where x is less than 32 di, is where the magnetic vortices occur. My specific project was focused on the right half, which is the magnetic island. The magnetic island is centered on the third quartile, which is 48 di. At T naught equals 15 omega IT, the magnetic island appears long and narrow. As time progressed, the magnetic island contracted, evolving from an elongated ellipse to a much rounder one, as displayed with these images on the right. It is better explained with the following animation. The left half of this simulation, which is blacked out, shows the expansion of the magnetic vortices. The right half is the magnetic island. As you can see, it is centered on 48 di and becomes much rounder as the time progresses. So the contraction of the magnetic island is a decrease in the perimeter of the island. During the procession of magnetic reconnection, an elongated magnetic island will gradually become rounder due to its internal magnetic tension. Magnetic tension arises from magnetic pressure, which arises from magnetic energy. What the contraction of the island means is that the major axis, which is denoted as B in the image on the right, would decrease to R, and the minor axis, denoted as A, would increase to R. The area is approximately constant during contraction due to the near incompressibility of the plasma, and the perimeter would decrease. This process is what I call the contraction of the magnetic island. In theory, plasma is incompressible, and in our simulation, it is nearly incompressible. But incompressible means that the area of the magnetic island is conserved, so that the initial area, which is pi AB, equals the final area of pi r squared. The area is conserved, but the perimeter of the island optimizes, and this optimization is a decrease. With this assumption of the incompressibility of plasma, the magnetic flux is conserved during contraction. Conservation of magnetic flux leads to energy gain. The magnetic energy is released during the contraction of the magnetic island. The particles accelerate due to the contraction of the islands. This acceleration leads to an increase in kinetic and thermal energy of the electrons. Here, the electrons gain energy by reflecting off the reconfigured field lines of the island, which behave as converging magnetic mirrors. The first step in my project was to calculate the expansion of the minor axis of the island. At first, this was done by plotting a cutting of the program at a fixed x-coordinate, which is the third quartile at each interval. It was this coordinate, since it was the center of the island, it should be the greatest distance. With this graph on the right, the horizontal axis is the y value and the vertical axis is the intensity. There are two peaks as displayed. The left peak corresponds to the bottom of the ellipse. The lowest Y value and the right peak corresponds to the top to the highest. In order to calculate the minor axis diameter, it is just the difference of these two Y values. I turned it into a program in IDL to be more precise and efficient. I printed out the data from this program from each interval and analyzed it using Excel. As you can see, the minor axis distance is the vertical axis, and the time interval number is the horizontal axis. The interval number ranges from 0 to 39, and its true time is denoted by interval number times delta t plus t naught. T naught is 15, and delta t is 0.5. Again, omega I is the ion gyre frequency. As displayed, this is a very linear trend with the growth with a correlation coefficient of 0.925. The next step was to determine the evolution of the major axis. Utilizing 3D images of the data, which I generated in IDL, such as the two displayed on the right, I located the horizontal endpoints of the island. The top image of omega IT equals 22 corresponds to the 15th interval, which is I equals 14, and the bottom image corresponds to the final interval of I equals 39. Instead of analyzing each interval's data, I used 14 intervals with each step as 1.5 omega IT. This corresponds with every third I value. Again, this is the linear trend expected with a high correlation coefficient of 0.9771. So as aforementioned, as the perimeter optimizes, it decreases, approaching the perimeter of a circle when the minor axis equals the major axis. Using the same 14 intervals as the major axis contraction, I generated this plot for the perimeter, and I approximated the perimeter by the expression displayed at the bottom left-hand corner. As displayed, this has a high correlation coefficient of 0.981 with the trend expected. Here in the final interval, the end minor axis radius is 2.165 di, and the end major axis radius is 7.95 di. This is just to say that this was not the complete contraction of the island, as A does not equal B. From here, it is time to calculate the magnetic energy that the contraction of the magnetic island releases. The release in magnetic energy, which is denoted by delta E, is estimated by the initial energy minus that of the final. And the initial energy is the square root of the magnetic field times the area, which is displayed in this first expression. The second expression takes advantage of the magnetic flux conservation, this constituent relation, that the initial minor radius times the initial magnetic field equals that of the final. Therefore, it can be rearranged in terms of the initial magnetic field. So with I corresponding to the first interval and F corresponding to the final interval, delta E is approximately 7.12 times the square root of the magnetic field times pi. However, the proportion of the energy released compared to its initial internal energy, which is delta E over E sub I, is much more applicable, as it is not dependent on the initial magnetic field. So taking delta E as defined previously, with E sub I as the internal magnetic energy at the start of magnetic reconnection, they can be rearranged to 1 minus that ratio. So using the same initial and final intervals as before, this shows the trend of 0.7288. So magnetic reconnection rearranges magnetic field lines and converts magnetic energy to thermal and kinetic energy via particle acceleration. As the magnetic reconnection evolves, the island contracts due to its internal magnetic tension. And during this contraction, the elongated magnetic island becomes rounder, with the area of the islands preserved since the plasma is nearly incompressible, but the perimeter of the magnetic island decreases, which leads to the contraction of the island. This contraction yields a release of the magnetic energy. And within the time frame that I analyzed, which are 40 time intervals from 15 to 35 omega IT, the magnetic island releases approximately 73% of its magnetic energy due to its contraction, converting it to thermal and kinetic energy. These are the sources which I used. And at this time, I would like to thank my mentor, Dr. Chair, and her graduate student, Chris Crawford, for their guidance and assistance over the summer. Thank you.
Hi, my name is Flasny, and thank you for watching this video. Make sure to follow us on our social media at CPHUL on Facebook, LinkedIn,